Hello and welcome. In this video, we'll be discussing how we can do inference with the different parameter estimates in our regression equation. Now, that might sound fancy, but think hypothesis tests and confidence intervals for our predicted slope and intercept. All right, let's get started. So, as we work through this, we're going to be coming back to the PE, SE, and CV notation for our hypothesis tests and confidence intervals, and we're going to be sticking with this largely through the rest of the course. Recall PE stood for point estimate and was our single number best guess. SE stood for standard error and was the measure of variability for our best guess, and CV was the critical value and came from a distribution. Remember, the reason that we do hypothesis testing is to help in our interpretation. For our interpretation, if we have a significant finding, we have evidence that the relationship is due to something more than just chance. So when we just look at the number, the question becomes, well, is this just a random finding, or is this actually indicative of an underlying pattern? And our hypothesis test helps us to determine that this is something that's an underlying pattern in the population. And again, remember, that's the goal for everybody. Nobody cares about what happened in the sample, or very rarely is that the case. Normally, what we want to do is take values from the sample and use them to make an informed decision about the population. Confidence intervals can be extraordinarily helpful in this case by providing a reasonable range. So remember, hypothesis tests are about making a decision. A confidence interval is about providing a reasonable range for the value. So as we discussed in the previous video, when I have a confidence interval for, say, my slope or my intercept, I interpret both the top and bottom sides and essentially everything in between to figure out the best and worst case scenario. Ideally, those align. Best case scenario, we make a lot of money. Worst case scenario, we still make a lot of money. That's fantastic and a great, easy confidence interval to interpret. The top and bottom really don't have a different interpretation pragmatically. But that doesn't always happen. And if that doesn't happen, it's worth remembering that both of the cases and everything in between is reasonable. So it's reasonable to expect we lose money. It's reasonable to expect we gain money. Well, you might make a different business decision under the impression that both of those outcomes are reasonably expected given the data. And that's the utility of the confidence interval, is it gives you what, based on the data, could we reasonably expect. So these use the same stats foundations as each other, but remember, interpretationally, confidence intervals give the same answers as two-tailed hypothesis tests. So remember, it's not just that CI and HT use the same pieces of the point estimate, standard error, and critical value, but they also provide the same interpretational evidence. Typically, evidence with non-significant tests or cases with non-significant tests in the hypothesis test will have intervals where the best and worst case conflict. So for instance, we have not enough evidence to determine a significant relationship between marketing and profit. Well, in that case, the interval will essentially say that as we increase the marketing budget, the profit could decrease or increase. And that is the joint interpretation, that to say, when my hypothesis test comes back non-significant, always the confidence interval is going to come back with a mixed interpretation, or the corresponding confidence interval to the two-tailed hypothesis test done with the same level of confidence. It's always going to come back with that style of mixed interpretation. In those cases, typically we just say, there was a non-significant finding. We don't have enough evidence to determine which way this is going to go. And so we don't do that. Sometimes what we do in those cases is just leave the confidence interval and say, this is the reasonable range that we think based on data. But again, because we don't know that increasing marketing is going to help or hurt profit, we're not really going to interpret that one way or the other. That is, I'm not going to interpret a statistic that says it'll help if it's reasonable that it won't help. All right, so in regression, we have two sources of error, and we've already talked a little bit about this in this course. So one is the idea that the sample line doesn't match the population line perfectly. And we've mentioned the idea of this when we talk about point estimates versus the population value, and our point estimates are never perfect. But in regression, we actually have another source of error. That is, our line doesn't perfectly align with each of the data points. Now, this second type of error is denoted sigma squared, and this is true even if the line is the perfect line based on the population values. At the end of the day, a single line just can't capture all of the variability of the data points, and that's okay, that's expected. So in a sense, this is kind of irreducible error that we can't do better. Of course, in our sampling line matching our population line, if we do collect more information in our sample, it'll get closer and closer to the population line, which is fantastic. It's worth mentioning, I say this is true in regression. This has actually always been true. We just haven't really had the opportunity or the framework to call this out explicitly. That second type of error is unavoidable. That is, we're never going to perfectly predict each data point with a group mean or with a regression line. And this is going to serve as the foundation for our other error terms. So the sigma squared, get used to that notation. We'll estimate that value, the sigma squared, the line not aligning with each data point, even if the line were perfect. We'll estimate that from the sample using the mean squared error. The other notation for the mean squared error is going to be S squared. Now, this is important because we're going to use this a lot. So get used to this, put a star next to this and write it down. We're going to use this a lot in this lecture video. I should note that the mean squared error is the same quantity as the mean squared error from our ANOVA table. So remember our error row, we had the sum of squares, degrees of freedom, and the mean squares. So the mean squared error, this is the same thing. Except now we're in a regression context. Again, sometimes you'll see it as MSE, but sometimes you're going to see it as S squared. Now, we're also going to use the quantity S, or the square root of the MSE, or the square root of S squared, and that's sometimes called the standard error of the estimate. This is actually going to be a foundational piece in a lot of our significance testing. So these are really important things to keep track of. We'll talk about how we can calculate these, and again, it's going to feel very similar to your ANOVA table, but it's really important to track that the MSE is denoted S squared, and S is just the square root of that. All right, so first of all, let's talk about the building of some of the regression components. And a lot of this regression components in regression for the inferential testing in regression comes from the fundamental ANOVA identity, but a specific form of it. It's the fundamental ANOVA identity as it relates to regression. So it's going to feel very similar. We're going to have a sum of squares total and a sum of squares error, but the components are a little bit different. So for instance, in the sum of squares total, as opposed to having y sub ij minus y dot dot bar, we have y sub I, each person's data point, minus y bar, the average of all the data points, squared and added up. Now, instead of sum of squares between or sum of squares treatment, we're going to have sum of squares regression. This is the sum of squares associated with the regression model. Essentially, for this one, we're going to take each of the predicted y values for each data point and subtract the grand mean and square that. Next, we have the sum of squares error. And if you think about errors, that is the difference between what we predicted and what actually happened. That's literally what this is. We take what actually happened. We see how far apart it was from what we predicted. That is what actually happened. Y, what we predicted, y hat, the difference between them, y minus y hat. We square each of those and we add them all up. And we get this quantity, the sum of squared error. Remember, SS stands for sum of squares, y is our observed values, y hat is the predicted values, and that y hat, we wrote an equation earlier, y hat equals b0 plus b1x. That's completely true here, just b0 plus b1x. So again, we use all these values. The SSE is going to be very, very big and useful in calculating the sum of squares error. So as we look at this, that sum of squares error, remember, the SSE, sum of squares error, is going to be very useful in calculating the standard error. So we're going to be using that a lot. And think about the sum of squares error is kind of the foundational component of the mean squares error. So as I mentioned, that kind of comes into play here. All right, so let's look at some of the notation. Now that we have the equation for the sum of squares error, and what's the equation for the sum of squares error? Well, we find the one on the right of this big equation in the middle of the screen here. Take every data point, subtract its predicted value, square that, and add it up. That's the equation for the sum of squares error. Now that we have that, we can write the equation for the rest of the things. So the sum of squares error, this is what we have from the previous slide. Now notice this, I'll mention the second notation, the sum of E squared. So this is the first time we're introducing the notation for the residual. So remember, the residual is denoted E, whereas the population error is denoted epsilon. The residual E refers to the observed in the sample errors. So here, E is y minus y hat for every value I. So E sub I, y minus y hat for that particular ith value. So instead of writing y minus y hat, sometimes we'll just write E. And so y minus y hat squared will be E squared. So the sum of squares error is all of the errors squared and then added up, sum of the squared errors. The degrees of freedom in this case is going to be n minus p minus 1. Now, p is the number of independent variables, and that might sound weird in simple linear regression where we only ever have one independent variable, and you'd be right. In simple linear regression, p is always 1, and so for this chapter, the degrees of freedom error is going to be n minus 2. But in general, the formula is n minus p minus 1. So if you learn it that way this time, then when we get to multiple linear regression, it's going to be the exact same thing. And just remember, p, the number of independent variables in simple linear regression, is 1. So this will be n minus 1 minus 1, which is the same thing as n minus 2. Our predicted fundamental source of error, that sigma squared hat, is going to be denoted s squared, and that's that MSE. To find that, we take the sum of squared error and divide by the degrees of freedom error. And that's it. It's the sum of squares error in the first bullet point or on the previous slide divided by the degrees of freedom error in the second bullet point, and that's our MSE, or s squared. Again, a main quantity that we're going to be using throughout, that s squared, and s, the square root of that. So whatever number s is, just take the square, or excuse me, whatever number s squared is, or the MSE is, just take the square root of that, and that gives you s. And that standard error, the estimate, is going to be the key component in finding the standard error of the slope and intercept. So again, we're going to be working through this. And as we do, if you're working through on your own problem, the first step is going to be to find that s, and then we're going to move on. So you need to find the sum of squares error, the degrees of freedom error. You take the ratio of those two to get the MSE, and then you take the square root of that to get s. And that's kind of your starting place. This is kind of the foundation for all of the other sum of squares, the sum of squared slope, the sum of squared intercept, etc. Or excuse me, the standard error, the other standard errors, the standard error of the slope and the standard error of the intercept. All right, so let's talk about the intercept first. It's worth knowing that the inference and intervals on the intercept are rarely done. And so I'm going to include it here, but just realize that there's not going to be a ton on this. And it's because we typically don't worry too much about this. Mostly people are interested in the relationship between x and y, and what is the value of y when x is 0 is usually not a particularly, it's not that it's not interesting or potentially useful, it's just not a question that a lot of people chase after. And so typically we don't do tests or intervals with this, but it's not that we can't. The point estimate for this is going to be b sub 0, or our best guess, the intercept calculated from the data. And remember, we wrote out this equation in the simple linear regression section. So this is just that same thing, y bar minus x bar times the slope. I think, no, double check that. The standard error. So normally we would write like SE here, but what I'm going to do for this notation, And this is very common for this notation, is I'm going to do S sub B0. And what that's going to represent is the standard error for B0. So you could do SE sub B0. I'm using S because that's, I don't know, that's common notation for this case. So in your equations, you're going to see S sub B0 and just realize that's the standard error for the intercept. And similarly, later on, you're going to see S sub B1. That's the standard error for the slope. Another reason I do this instead of just writing SE like we did in previous cases is now for a single problem, we're going to have an intercept and slope. And we're going to need a standard error for the tests of both of them. So in a single problem, we're going to have multiple standard errors. And so we need notation to help with that. Again, we could use SE sub B0. I'm just going to write S sub B0 instead. Notice that this is S, the previous value, that square root of the MSE that I said was going to be important. That's the starting place. I take that value S, and then I multiply it by the square root of 1 over n plus x bar, that's the mean of all the x values, squared, divided by x minus x bar quantity squared, and then added all that up. So we already have that bottom, that denominator from our previous calculations, but I don't think we found x bar squared yet. The critical value, typically we do two-tailed critical values unless we have reason to believe otherwise. We can do one-tailed stuff, but we're getting to the point where I'm just going to start defaulting to things like point estimate, the null hypothesized point estimate 0, and the critical value is a two-tailed critical value because these are very, very standard things. Same thing with alpha. I'm probably going to start defaulting more and more to alpha equals 0.05 because, again, that's just very, very, very standard to happen. So remember, for the two-tailed critical value, that's for a two-tailed hypothesis test, and that's for confidence interval. So that'll be where critical value comes from. Though again, hear me say, you can still do PE sub 0 is something different than 0. You can still do a two-tailed or a one-tailed test with this if you want to. Just put all of the alpha in one tail. Y'all know how to do this, and you know we're getting kind of advanced. I think I can say you know how to do this from your previous problems, and I think you probably do know how to pull those different critical values, and we'll just compare those test statistics to the appropriate critical value. All right, so PE sub 0, SE sub 0, and CV. These are the pieces that I need to go on and build my stuff. The rest is going to feel very familiar. And honestly, y'all, I'm not going to make a big fanfare of it. The hypothesis test, we have the null hypothesis compared to PE sub 0. Remember, PE sub 0 is usually 0. The alternative hypothesis, greater than, less than, not equal to PE sub 0. Note I'm comparing the population value because my hypothesis tests are about the population values when I'm doing that. Test statistic, point estimate, minus null hypothesized point estimate over the standard error. And again, because the null hypothesized point estimate is typically 0, plugging in my PE and SE from my previous slide, I have B0, the point estimate, divided by the standard error of B0, S sub B0. And that's my equation. Now, again, are those longer? Well, yeah, the B0 is the Y bar minus X bar times the slope. And the standard error is that S times the square root of all that stuff underneath the square root. I don't even remember it all. And so, you know, these can be written out in longer terms, but remember, once you have the point estimate and the standard error, you just put those in those places. And we compare to that critical value. Again, I wrote it out as a two-tailed critical value, but just like before, it can be a one-tailed critical value if you want to do a one-tailed test. Pretty straightforward, right? I mean, like, we don't need 18 slides to explain this anymore. Y'all are hopefully getting the hang of conducting hypothesis tests based on the point estimate, standard error, and critical value. Same thing with confidence interval, y'all. Point estimate plus minus standard error times the critical value times the standard error is typically how I do it. So I don't know why I wrote it backwards this time, but just flip that critical value and standard error. I apologize. Point estimate plus or minus the critical value times the standard error, and that's our case. So yeah, pretty straightforward. I hope you're getting the hang of it and start to feel more and more confident about running these tests and the components of these tests and how we construct things like hypothesis tests and confidence intervals. With that, now let's do inference for B1 or beta 1. And I'm going to, again, just kind of go through these. And these are relatively straightforward once you have them. Just need PE, SE, and CV, and we're good to go. I will say the inference for the slope is very common. So I mentioned earlier, inference for the intercept, not very common at all. We typically don't do that. But for the slope, inference is very common. We do this very often. Why do we do this? Well, because the inference for the slope actually doesn't just test the slope, and this is kind of cool. Inference for the slope also tests the linear relationship between x and y. If it has a statistically significant slope, then it will have a statistically significant relationship between x and y. If it doesn't have a statistically significant relationship, or if it doesn't have a statistically significant slope, there is no statistically significant relationship between x and y. So what's interesting here is that this result talks about the general relationship between x and y, and is actually, I'll say, mathematically identical to the correlation in the sense that it'll give you like the same test statistics and p-values when you do the comparison. So if you do the comparison to the slope, it's going to give you the same p-value as doing a test of correlation. And so that's why people are very interested in tests of the slope, is because the test of the slope is synonymous to a test of linear relationship between x and y. If there's a significant slope, there's a significant linear relationship between x and y. And if there's not a significant slope, there's not a significant linear relationship between x and y. All right, so for my point estimate is B1. That is my slope equation from earlier when we did the simple linear regression stuff. That sum of x minus x bar, y minus y bar divided by sum of x minus x bar quantity squared. The standard error, again, I'm denoting as S sub B1, so that indicates this is the standard error of B1 instead of the standard error of B0. And that's just going to be that S value, kind of the starting place, divided by the square root of the sum of x minus x bar quantity squared. So we're seeing a lot of that sum of x minus x bar quantity squared pop up over and over again. Critical values, same critical values as we had before. T-distribution, the degrees of freedom or the degrees of freedom error that we talked about calculating a few slides ago. And you can do a two-tailed test or a one-tailed test or whatever. Remember, two-tailed test and a confidence interval both use the same cuts. Confidence interval is always two-tailed, but you can also do a one-tailed test for cutoffs too. As before, use these to run the hypotheses test, and y'all, I'm not going to spend a lot of time going over this because this is the exact same thing as what we had before. Heck, you can see how much I copied and pasted because I even mixed up the critical value and standard error in that confidence interval equation. I typically write them in the same order. It doesn't matter because multiplicatively you can alternate the order. So technically it's mathematically right, but it is a bit confusing. So I typically do PE plus minus SE times or plus or minus the critical value times the standard error. And that's what I do in the second bullet point in the confidence interval. Sorry about that. But yeah, it's the same process for hypothesis testing as we've always had in this course. Same process for confidence intervals. The only new thing is finding the point estimates for each of the things, and that's not even new. So really the only new thing is finding the standard error of the intercept and the standard error of the slope. First, calculate that S, and then go to those respective standard error equations and calculate those. All right, well, let's jump into this in our marketing example. So the goal is still the same, looking at the relationship between marketing and profit. But now I want to add inferential components. That is, I want to do hypothesis tests and confidence intervals, because rather than just seeing what happened in the sample, I want to see, is there enough evidence from the sample to make determinations that these relationships exist in the population? With a hypothesis test, I want to determine of the slope, I want to determine, is there enough evidence from this data to determine that marketing is related to profit at all in the population? And with the confidence interval, I might want to describe a little bit more about that relationship. Just how related are they? As marketing goes up by a certain amount, just how much would I expect in the population for the profit to go up? What would be reasonable to expect based on the data? So that's how I'm going to use my inferential statistics here. The steps is going to look something like this. First, we're going to find B1 and B0 to make the estimated regression line. So we already did that for this one, but if I'm working on a raw problem, that is the first step. I have to find B1 and B0, and I have to make my estimated regression line equation. Next, I have to find the predicted values, and all of this eventually is going to have to do with the error. But if I don't have my predicted line, that's bullet 1, and I don't have my predicted values for each of my observed x values, that's bullet 2, I can't calculate my errors, and so I can't do my inferential tests. Here, in the second step, I'm calculating those predicted y values for each x value, and I'm simply using the equation that we wrote down earlier. The predicted y is the b0 and b1 from step 1 with b1 times x. Now that I have my predicted y values for every data point, I'm going to find the difference between the observed y's and the predicted y's for each data point. I'm going to take those differences, again, errors, how far off was my line predicted from the actual observed data point. I'm going to take each of those and I'm going to square them and then add them up, and that's my sum of squared error. From here, I have everything I need to start building out my MSE, calculating the square root of that to get s left alone, and then using that to find my standard error of the slope, standard error of the intercept, which is the last piece that I need in order to do my hypothesis tests and confidence intervals for both the intercept and slope. Woo! All right. It's a lot, so let's get started. So for my best fit line, again, I'm not going to redo this work, but if you want to see it, go back, check out the last lecture video, and you'll see how I calculated my best fit line for this equation to be y hat equals negative 2.7683 plus 0.6125 times x. With this, I'm now going to find all of the predicted y hats for each data point that I have in my sample data set. To do this, I'm simply going to plug in the x values, type enter on my calculator, and then find the predicted value of y for that particular x value. So for instance, if I have a data point of 1, I would plug in 1, or x equals 1 for one of my observed data points. I'd plug in 1 for x, solve that number, or do 0.6125 times 1, and then do negative 2.7683 plus that, and that gives me my y hat for that particular x value, and I just jot that down for that particular row. Once I have that, I'll find the residual, the distance between the observed y and that predicted y hat that we calculate. I'll square that difference, and then I'll add them all together to get that sum of squared error. My table might look something like this. I have my x and my y value. In a third column, I'll do that b0 plus b1x. So I'll take each x. So for that first row, that'll be my 6.3. I'll plug it in for x in that top equation, y hat equals negative 2.7683 plus 0.6125, the one at the very top of this slide. I'll plug in 6.3 in for x there. I'll solve that, and then that becomes the first number in this third column, 1.0905. For the second number in the third column, I do the same thing, but now I plug in 6.9 for x into that equation at the top of the slide, hit enter on my calculator, and I get back 1.4580, and I do that for every value in my sample. Once I have that third column filled out, now I'll move on to the fourth column. For the fourth column, I'll take the y value in the first row 2, I'll subtract the y hat value in the first row 1.0905, and I'll just hit enter on my calculator and get whatever difference that is. In this case, that number is 0.9095, and I'll do that for each observation in my sample. After I fill out the fourth column, then I take whatever number's in the fourth column and I raise it to the second power, and that's how I get the fifth column. That is my squared errors. Finally, not shown here, I'll sum up all of those squared errors to get my SSE. After adding up all those squared errors, when I add up every number in that fifth column, I get 7.8726. All right, so now I can keep moving. I need my N, sample size, that's the number of observations I had or number of people I talked to, in this case 7. I have only one independent variable, so I'm going to get P equals 1. My degrees of freedom are going to be 7 minus 1 minus 1, or 5. And then I have my sum of squared error calculated at the top based on the previous table, my degrees of freedom error calculated in this third bullet point to be 5. I take the sum of squared error divided by the degrees of freedom error, and I get this S squared, sometimes called the MSE, which is 1.5745. As a pause, if you remember the MSE in ANOVA, remember the MSE was the SSE over the DFE. So this equation is exactly the same as what we did in the ANOVA chapter. Now we're just doing it in the context of regression. Again, S squared is cool, the MSE, but what I really need as the basis for all of my standard error calculations for intercept and slope is S. So I'm going to find S by taking the square root of that S squared value in the fourth bullet. So the S squared was 1.5745. I take the square root of that just by typing that in my calculator and hitting square root, or using SQRT of 1.54 or 5745 in R, and I end up getting 1.2548. This is kind of the foundational standard error that I'm going to be using and modifying for my standard error of the intercept and standard error of the slope. So this is like the starting place. All right, so based on the tables from way back in correlation, I also get that my sum of x minus x bar, which again is bizarrely, oddly often used, is 15.51, and x bar is 7.9714. Last but not least, I'm going to go get my critical value from tables or R. I'm going to use my degrees of freedom of the error, which is 5. I'm going to take my alpha and divide by 2, so that'll be my two-tailed test. I'm not going to specify whether this is a positive or negative relationship. I'm going to test either way, and that way I can just reuse this for my confidence interval 2. My critical value turns out to be plus or minus 2.5706. And now I have all the pieces I need to start doing these calculations. So first of all, I'll go on and make my point estimate and standard error. So the point estimate is just based on that first equation. I pulled that from our simple linear regression section when we were talking about that. For the point estimate, I have negative 2.7683. And again, this is just the best guess I can make from the sample as to what my intercept is. The equation for this from the last section was something like y bar minus x bar times the slope. And double check that. Again, just go back in your notes and check that. All right, S sub b sub 0, that's my standard error. This is going to be that starting place S times the square root of 1 over n plus x bar squared over sum of x minus x bar quantity squared. So plugging in my numbers from the previous slide, I plug in 1.2548 for S, 7 for N, 7.9714 for X bar, which is the mean of all the X values, and 15.51 for X minus X bar quantity squared, sum all that up. Hitting enter on my calculator, I get S sub b sub 0, or the standard error of B0 is 2.5837. And combined with the critical value that we calculated on the previous slide, or listed in the previous slide, I now have my point estimate, standard error, and critical value. Again, the big calculation that we're adding here is that standard error calculation. All right, so for the hypothesis test, my null is going to be the intercept is 0. My alternative is going to be the intercept's not 0, two-tailed, not specified. My test statistic, I take the point estimate minus the null, which is 0, over the standard error. I'm just listing out PE sub 0 in the equation. Guess we got to do it once, so we'll do it here at the end. No, it's not quite the end. I guess we have a whole nother lecture set, but we're getting close. This regression stuff is kind of the end. All right. Anyway, we have our point estimate, negative 2.7683 over the standard error. And looking at this, that gives my test statistic to be negative 1.0714. So my critical value range, 2.57 and negative 2.57, negative 1.704 is inside of these values. So it's not in the extreme range. Because of this, I went in thinking that the intercept was 0, and I didn't see anything to change my mind. So not enough evidence to reject the null hypothesis. Again, is it meaningful to test the intercept against 0, to test what the y value is on average when x is 0? To test if that is 0? It really depends on your context. In fact, that's another reason I mentioned PE sub 0 in this equation a little more explicitly than I normally have in this course, because especially for the intercept, testing the intercept against 0 that just has to be a very specific situation for that test to be meaningful. By the way, I'll say most of the built-in tests in software do this test by default. And that's another reason why people just tend to ignore these tests, is because built-in, it compares to 0, which is kind of a silly comparison in most applied situations. In any case, in our case, there isn't enough evidence to conclude the intercept is different than 0. For the confidence interval, maybe a bit more useful. I take the point estimate plus or minus the critical value times the standard error. Plugging in those pieces, I get that this is anywhere between, the intercept is anywhere between, population intercept, negative 9.41 and positive 3.87. And again, that's kind of the statistical interpretation, that the population intercept is anywhere in that. But we can do better. We can do better. So first of all, as this contains 0, the null hypothesized value in the hypothesis test, we say 0 can't be ruled out. 0 is in the reasonable range. So I can't call 0 an unreasonable value. Not enough evidence to change your mind away from 0. But we can interpret this in the context of the problem. So what's the context of the problem? Well, remember, an intercept is the case when our X value, or in our problem, marketing budget, is 0. The Y value, the profit, is between negative 9 and 3.8. So we're saying essentially the profit is negative or positive when we don't have a marketing budget. So marketing budget equals 0 means no marketing budget, and negative profit would mean we lose money. Positive profit would mean we gain money. So we're either going to lose or gain money with no marketing budget. This isn't very informative. And as we said, with a non-significant hypothesis test, this is common to see with confidence intervals, that they're not particularly informative. So typically we just say this isn't significant and we don't interpret. And again, let me say this one more time. When we have a non-significant test of a parameter estimate, in this case the intercept or the slope or anything else, we tend to not then interpret our best guess. So our best guess in this case was negative 2.76. I wouldn't say the intercept, there's not enough evidence to determine it's different than 0, and then go interpret that on average we're going to lose $2,768 if we don't have a marketing budget. That would assume that we have evidence to believe that there's a loss. And in this case, we don't have evidence to believe that it's any different than 0 at all. That is, there might not be a loss at all. So typically what we do in terms of interpretation is we start with our significance test. If it's significant, we go on and interpret, and usually provide a confidence interval so that we know the relative reasonable potential magnitudes in any direction, the best and worst case scenarios, reasonably based on our data. But if it's not significant, we just leave it. We say there's not enough evidence to know if no marketing budget is going to be good or bad, and then we let it go from there. All right, well, let's work on our slope. So for our slope, our point estimate, again, we calculated this previously. This is from the previous section when we were calculating the basic line. Our standard error, again, we're denoting the standard error of the slope is S sub B1, and this is that S over the square root of sum of x minus x bar quantity squared. I just plug in my numbers from the previous slides and get 0.3186. Yay! Combined with the critical value, now I have the point estimate, standard error, and critical value needed to do my tests. Now, in contrast to the test of intercept, which again, testing against zero doesn't tend to make sense. In a slope, testing against zero can make a lot of sense. And again, zero implies no relationship. So a general test against zero says, is there a relationship at all between x and y, a linear relationship? Here, plugging in my values, I end up getting a test statistic of 1.9225. Again, the critical value is the same as before. And because 1.9225, while it's bigger than my test of the intercept, is still inside of my reasonable range, essentially. It's not in my extreme values as indicated by those critical values. It's not in that extreme area part of the distribution. In this case, that means there's not enough evidence to change my mind. I came in thinking marketing and profit weren't related, and this example didn't have enough evidence to change my mind. And that's kind of fascinating in this case, right? It kind of goes against a gut check. That's okay. That just means there isn't enough evidence. That doesn't mean that there's evidence that they're not related. That's not at all what we're saying. It means that there's not enough evidence. What might we need to do? Well, we might need to go and get more evidence in this particular case. All right. Again, it's worth mentioning that there's two joint interpretations here. One is there's not enough evidence to determine a non-zero slope. So not enough evidence to determine the slope is significantly different than zero. But again, that conjointly means that there's not enough evidence to determine that there's any linear relationship between x and y. So remember, we're kind of testing two things with a single test, and this has two interpretations on the slope itself, which is kind of the straightforward interpretation, but also on the perhaps more important interpretation of, is there a relationship at all between x and y? All right, so for the confidence interval, I just have my equation, I plug in the stuff, and here's my reasonable range. Again, zero relationship is reasonable. So yeah, we can't rule out the null hypothesis we're stuck with, or we retain the null hypothesis, fail to reject it, however you want to say it. Came in believing no relationship, haven't changed our mind. In the context of this problem, essentially what this means is as I add a marketing budget, there's not enough evidence to convince me that our profit is going to go up. In the confidence interval, it's reasonable to believe that my profit could go down if I add to the marketing budget, or that my profit could go up. Again, this isn't informative, conflicting information. And again, that typically is what our confidence intervals look like when we have a hypothesis test that's non-significant. So typically we say there's not a significant relationship between marketing and profit, and we leave it there. But again, what does that actually mean? It means that marketing could make profit go up or down. We don't know that it's going to make it go in one direction or the other. Don't have enough evidence to believe that anyway, or make that conclusion. And remember, the conclusion is about the population. All right, so we just ran everything. Let's do a little bit of reflection. We have our best line, but neither the intercept or slope are significant. So we calculated the best line, and it is the best line that we have based on the sample data. But we don't have enough evidence to determine, based on this sample, that the intercept is anything other than zero. Remember, zero is the default starting place belief, and we didn't convince ourselves that it's different than zero. So just because we calculate a different sample intercept doesn't mean that we've convinced ourselves that the population is zero. So essentially, because neither of these are significant, I look at both of them as zero. Same thing with the slope. We didn't convince ourselves that the slope was different than zero in the population either. And when we treat that as a null hypothesis, we have to have evidence to change our mind. In this case, because neither are significant, I kind of look at this equation and assume by null hypothesis that both the intercept and slope are zero, even though we calculated that differently in the sample, because we didn't have enough evidence from the sample to make a determination of that existed in the population. So for the intercept, diving in based on the confidence interval, again, we could reasonably have anything between a $9,000 loss or a $4,000 profit without a marketing budget. That's my intercept interpretation. Again, this is one component of an argument, so other things come into play. Hey, could we have any profit at all without a marketing budget? Maybe, maybe not. There's a whole ton of things that go into this, but this is one component, kind of the naive interpretation, and we can upgrade from there. If we increase the marketing budget, we could reasonably see anything between a few $100 loss or $1,000, $1,500 profit as the marketing budget increases based on this. So again, we're using just a few data points to make an inference across all of our marketing planning, all of the potential marketing campaigns, all of the marketing campaigns represented by this sample. So we're making large-scale conclusions based on a few data points. And essentially what this is saying is, given the wide range of options, we didn't have a lot of data. So we could go collect more data. We're going to see those confidence intervals narrow. That doesn't mean they're going to move in the direction we want. That doesn't even mean they're going to stay where they are, but they are going to get a little more precise about whatever those population values are. I will say a big takeaway here is to always check significance before interpretation. So sometimes what happens for people who aren't used to this is they'll run the best fit line, that top bullet point there, and they'll say, oh, okay, well, with no marketing budget, we're going to lose money. But as we increase our marketing budget, we're going to increase profit. And that is the point estimate interpretation. But after the significance tests came back, we realized our sample doesn't provide enough information to make the determination that we're going to lose money without a marketing budget at the 95% level, confidence level, nor does our sample provide enough information to make the conclusion that our profit's going to go up if we increase the marketing budget at the 95% confidence level. That is, while this is the best guess from our sample doesn't really have enough information to tell us much at all. We don't know if we're going to lose or gain profit when we don't have a marketing budget. And we don't know if increasing the marketing budget is going to lose or gain us money based on this sample. We're really in the dark because our sample didn't have a ton of information. And heck, even if our sample did have a ton of information, we're still in the dark. Like we're left in kind of this awkward limbo place. That is the correct conclusion from this data. And again, this is what I mean in this last line when I say it's important to check significance before interpreting. The wrong interpretation is looking at the top bullet and thinking that that's enough information to make a conclusion. What our significance tests tell us is actually that is not enough information to make a conclusion. The conclusions implied in that equation, that is, that those patterns we'd expect to see in future data or in the population in general, that's an incorrect implication to say. We, now that we've done the tests, know that we don't necessarily expect to see those patterns in the population. And because of that, I might not present the results of that top bullet because they'll be deceptive to someone who doesn't understand this. Someone who doesn't understand this might think that I do expect to see that pattern in the population, when again, my hypothesis test says no. There's not enough evidence to know that there's any pattern at all in the population based on this sample data. So for me, the conclusion is I checked the significance before my interpretation. So I ran the model. I have to calculate B0 and B1 to be able to check significance anyway. But when I check significance and it's not significant for both the intercept and the slope, I might not present the regression model anyway because it's deceptive. That is to say, I don't have evidence that the intercept is anything other than 0 or that the slope is anything other than 0. And because I don't have that evidence, well, this equation may as well not exist. It doesn't really tell me anything at all regarding the population. By the way, that's a very frustrating place for most people. I just collected a bunch of data, just did a bunch of analysis. And remember, we did it all by hand, but in R, it's going to take half a second, as long as you can have the raw data to use built-in functions. But I just did all this data collection. I just did all this analysis, and I can't make any conclusions. And yeah, that's right. That's right. We don't have enough evidence to know what's going to happen if you increase your marketing budget based on that data. So be careful. And that's the correct conclusion. That is a correct conclusion. This is a little philosophical fortune cookie-y, but it is wise to know when you don't know. So it's a good thing to know when you don't know what's going to happen, and to be able to acknowledge that. In that previous case, statistically, we didn't know. Ooh, all right. Well, now might be a good time to potentially take a 5-minute break, but B, pause the video and come back and try it on this data set. So again, you've done a lot of work on this. You've built the correlation table that has that x minus x bar squared and that sum. You've already built the regression equation. You've already found B0 and B1, the point estimates in our tests of the slope and intercept. So you've already found all that. You've already found B0 and B1 for the y hat for finding the predicted values. So you've already done a lot of work on this. You have two options with this one. You can kind of start again and see, do I remember how to do all that? Because eventually you're going to have to do all of that again in your homework problems. So do you remember how to do all that? So you could try that out, test yourself and try to do the whole problem top to bottom. Or you could go in your notes, find the previous values and use those. That's kind of what I did in my example. Completely up to you as to how you want to approach it. In any case, go on and give this one a shot. You're going to build confidence interval. You're going to find the best fit regression line. You're going to build confidence intervals for the intercept and slope. And you're going to do hypothesis tests comparing against 0 in a two-tailed test for the intercept and slope. I want you to try all of that on your own and see how you do. Again, for a gold star, try interpreting this. Once you get there, once you get to the hypothesis test, once you get to the confidence interval, for both the intercept and the slope, try interpreting that and seeing if you can walk away with an applied meaning from that context. If you can, fantastic. And if you can't, well, at least you'll hopefully have learned something when we get to that together. In any case, go on, pause the video. It's been a long video already, so consider taking a 5-minute mental health break, and then come back to the paused video and try calculating all this yourself. After that, go on and play, and we can go through the answers together. So give it a shot. All right, let's come back to it and see how you did. So for our previous calculations, our best fit lines is 57.59999 plus 5.3574 times x. And that's our best fit line from earlier. So I'm going to need this to complete the table. Again, even for the by hand work, R is helpful, so you could use that if you want to. Make your x value and then do that line times x, which is the x vector of all the x values, and that'll give you all your y hats. In any case, I've got my y hats here, and you can just kind of double check for yourself if this lines up. I calculated it out to 4 decimal places. Again, software is going to be your friend. Do it by hand once to get a feel for it, and then software is just going to be so helpful. All right, so double check your work here. I got my y hats, my e. Remember, e is y minus y hat for each of the values, and then my e squared. So that's all those e values raised to the second power. My sum of squares error is summing up all those e squareds. So I get 58.6460. 8 in my sample size, only one independent variable. Degrees of freedom error is 6 in minus 1 minus 1. S squared is that sum of squared error that we found at the top, divided by the degrees of freedom error we found at the third bullet. I get 9.7743. S is just that S squared from the fourth bullet and the square root of that number. So I get 3.1264. And this is that fifth bullet, S. That's kind of my foundational piece for all my standard errors. From earlier, I have the x minus x bar squared is 67.76, and x bar is 3.9857. From R, I'm calculating that my critical value for T is 2.4469. And again, I'm using the two-tailed critical value for a two-tailed hypothesis test and my confidence interval. And for t, I'm using degrees of freedom error for my t. All right, so now we have all the pieces in place. My standard error, this is my work here, just plugging in the different pieces. Looks like I gave you all the answers for B0, SB0, and CV. So we all have the same starting place here. Again, doing a two-tailed test comparing to 0, it's a bit of a silly comparison for the intercept. Nobody really cares if my, well, I guess people do care if your pizza sales when students are not there are 0. This would be when students aren't there, are the pizza sales different than 0? Hopefully they are. And in this case, we have a really, really large test statistic. So yeah, they're significantly greater than 0. All right, so for the confidence interval, well, what is a reasonable range to expect pizza sales to be? And this is kind of interesting. I think this could be useful. I don't like the hypothesis test comparing to $0 sales when there's no students. But here's a question. In the summers, what do we expect the pizza sales to be? That is, when there are no students, what do you expect pizza sales to be? That could be a very useful question. So in this case, we expect them to be anywhere between $53,000 and $62,000. And again, that's for the population on average. So this doesn't contain 0. Again, we're not expecting to go out of business. Well, maybe, but we're expecting to at least have $53,000 to $62,000 in sales. What's our break-even point in terms of a business? How much sales do we have to get? Well, again, that's part of the broader, more complex contextual interpretation that we could and should apply in a real case. We don't know those answers, so we'll just say $53,000 to $62,000 in sales and let the applied people interpret that in an applied way. Is that good or is that bad? All right. Yeah, so the positive profit, not due to random chance. What's the reasonable range? Well, again, reasonable to expect between 53 and 62. Could it be outside of that? Yeah, it could. It could, but 95% confident that it's the average sales based on our data set, the average sales when there's no students, 53 to 62. Again, there is a little caveat here based on our previous lecture. Remember, the caveat here is we didn't actually have any data points that looked at when there were 0 students there. So we're extrapolating a bit for this. And yeah, that can have an impact just because, again, the behavior of what happens in that context can just be different. It can be completely different. So that's worth mentioning. What's an example? Well, again, I've got students in the different months that I have students on campus. But in the summers, all the students go away. Okay, well, I wouldn't just project to maintain all of my regular sales, even not including the students, because in the summers, sometimes regular families go away too. Like some people take trips, their kids are off school, a lot of people leave, we buy less pizza. So we might expect at that 0 student time for something maybe drastically different to happen in that pattern. So I might be a little bit careful here because I am extrapolating outside of the range of my data. That's one of those additional contexts we talked about. So here, based not accounting for that, $53,000 to $62,000 would be reasonable to expect in sales when there's no students. But there's more to it than just that. All right, for our slope equation, again, it looks like I gave you all the answers, but here's my work here. So I've got my point estimate, standard error, and critical value. I can go ahead and put together my test. Do get a very big test statistic here, so compared to my critical value, there is enough evidence to determine that there's a relationship between the student population and the sales. So that is to say there is enough evidence to determine that there's a non-zero slope in this case. And again, non-zero slope and there's a relationship between X and Y are synonymous. So those are the same test tells me both things. More interesting to me than is it 0 or after finding out there's evidence that it's not 0 is, well, what's the reasonable range? Where could I reasonably expect this to be? And looking at this, it looks like for every $1,000, I expect between for every 1,000 students, I expect between $4,000 and $6,000 in additional sales. Again, not 0, so that means saying students don't impact sales is not a reasonable thing. Reasonable is to expect it's anywhere between $4,500, say, and $6,000 in impact on sales. So yeah, context of the problem, company expected to make more money as the number of students increase, again, between $4.5 and $6.25 thousand for every additional 1,000 students increase. Other things, we talked about the range of the data. We didn't cost per transaction. So this is in sales, but that doesn't necessarily relate to profit. So, I have to consider how much does it cost to make a sale in terms of the ingredients to make the pizza, but also in terms of staff time, in terms of the location and building rent and electricity and the cost to heat the ovens and the cost for software to run pizza orders and just all this other stuff. So lots of other things to think about in this context. All right, well, let's close out our conversation on inference. So inference aids in interpretation, and inference is the process of hypothesis tests and confidence intervals. Those are inference in the sense that they take our sample values and try to use them to make an educated claim about the population. That is the process of statistical inference. So this is helpful because it aids interpretation by using the sample values to assess the evidence from the sample as a claim on the population. So that's very, very, very useful. Again, we look for things like, does this have enough evidence to make me determine that this is more than random, that this is indicative of an underlying population pattern? The other thing that I love about the inference is the confidence intervals. It gives me a reasonable range based on the data of where I could expect this pattern, be it the intercept or be it the slope, where I could expect that to fall reasonably. All right. And I guess for the confidence interval, I get to interpret the best and worst case scenario. So I like that a lot too for the confidence intervals. The reasonable range of where I'd expect the pattern to fall as a population pattern based on my data. So again, using the data to make an educated guess about everybody, what's reasonable to expect for everybody based on our data. And then I can do interpretation in the worst and best case scenario. And I keep going back here. When I say everybody, again, I mean the average over all people. So if it's the intercept, it's not on one particular day. It's the average across all of it. All right. So remember, inferential statistics tend to start by assuming that null hypothesis. All inferential statistics do, for confidence intervals anyway. And often that PE sub 0 that we assume is 0. So typically we assume that nothing's going on. No intercept is 0. We start by assuming that the slope is 0. No relationship between X and Y. And we talked about this a couple of times, but without significant findings, without evidence to change our mind, the default interpretation, and this is so important, so star this. I know this is long, but please star this. This is so important. Without a statistically significant finding, without stuff to change our mind, that null hypothesis that there's nothing going on, without something to change our mind from that, the default belief shouldn't be that the population intercept is whatever our sample intercept was, that the population slope is whatever our sample slope was. That should not be our default interpretation. Without significant findings, without something to change our mind, the default belief should be the population intercept is 0 and the population slope is 0. That's the whole idea behind the hypothesis test system. We come in with default beliefs that nothing's going on, and we try to change our mind from that. For some reason in regression, it's kind of tricky because we want to interpret that sample regression equation, that best line equation. But the truth is, if we run the hypothesis test and it's not significant, in place of B0 and B1, we should be plugging in zeros in both of those places until the results are statistically significant enough to change away from that null hypothesis of 0. So unless we have a significant finding, think about 0 as the B0 in B1, not whatever values you calculated when you interpret. And this is why we don't interpret those equations when they're not significant. Now, with that said, remember we can still use the confidence interval. Even with a non-significant finding, the confidence interval does still present a reasonable range that we would expect the population value, be it intercept or slope, to fall in, even if it's not significant. So if it's not significant, the confidence interval is going to have conflicting interpretations on the low and the high end, and that's okay. But we can still include that confidence interval to see the reasonable range that we would expect the intercept and or slope to fall in. Because of this, the interpretation flow should look at the hypothesis testing first. If the hypothesis test is significant, then we interpret the parameter estimates that are significant. And typically when I interpret the parameter estimates that are significant, I'll use the confidence interval to give me the low and the high value in my interpretation. So I'll not just interpret the significant parameter estimates, I'll interpret the low and high end of the confidence interval values for the significant parameter estimates to get a feel about what's reasonable to expect in the intercept and the slope situation. Alternatively, I could just look at the confidence interval, because remember, the confidence interval I can use to do hypothesis tests too, and then I could just interpret the confidence interval values. Remember, if it's not significant, your confidence interval is going to come up with conflicting interpretations, and that can be a problem and a little bit confusing. But you can just start with the confidence interval. You don't have to worry about doing the hypothesis test at all. The one nice thing about doing the hypothesis test is you don't get those weird conflicting interpretations of a confidence interval. You can just target the confidence intervals that are going to tell at least a positive or negative overall story, even if the size of the positive or negative effects are different in the reasonable range. So that's the argument for doing the hypothesis test first. The argument for doing the confidence interval anyway is, sometimes it's nice to know the reasonable range that this effect could come in, even if the test is not significant. Sometimes it's really, really close, and that reasonable range would show that. So there's an argument for including the confidence interval, kind of no matter how the hypothesis test comes out, significant or not. Ooh, all right, team. Well, this has been a big one. Inference in simple linear regression. So we talked about some of the inferential components. We did the point estimate, standard error, and critical value for all of our pieces. We talked about the place and role of inference and interpretation. And then we talked about doing a lot of the calculations, starting with that S value, the square root of the MSE, and using that to find the standard error of the slope and the standard error of the intercept. And then we, kind of closed out with a couple of different problems. I got to try one, and y'all hopefully took a break and got to try one yourself. So yeah, this has been a big one. Thanks for sticking with me in this. I think this was important, and we'll be using these pieces as we move forward too. But thanks for sticking with me through this video, and I will look forward to catching y'all in the next one.